Hello students and welcome to the course 21SMAC244B Polymer Analysis. In this course we are going to study the different analytical procedures used for the analysis of polymers. The first chapter in this course is Introduction and Identification to Polymers. The polymers are very large molecules made when hundreds of monomers join together to form a long chain. Polymer is a Greek word. Poly means many and mers means parts of the units. These mers or parts of the units are high molecular mass, each molecule of which consists of very large number of single structural units joined together in a regular manner. In other words, polymers are giant molecules of high molecular weight called macromolecules, which are built up by linking together of a large number of small molecules called monomers. The low molecular weight polymers having a small number of repeating units, generally 2 to 10, they are called as oligomers. For a polymer, the number of repeating units should be more than. Now, what is this monomer? The small individual repeating units or molecules are known as monomers. Monomers means single part. Imagine that a polymer is made of smaller units, that is monomer, which is represented by letter A. Then a polymer made of that monomer would have the structure as shown here. All the monomers will join together one by one and it will form a large molecular weight compound, and that compound or the substance will be called as the polymer. The monomers can have C double bond C or C triple bond C bonds, functional groups, or can also be a cyclic or a cyclic in structure. The different examples of monomers are butadiene, in which there is a carbon-carbon double bond is present, a styrene, a benzene ring along with a carbon-carbon double bond, ethylene glycol or ethylene epoxide, etc. All these monomers will join together to form a long chain of the molecules, and this long chain will be called as the polymer. Whereas the process by which the monomer molecules are linked to form a big polymer molecule is called as polymerization. The polymerization is a process of bonding monomers or single units together through a variety of reaction mechanisms to form longer chains named polymer. As an important as polymers are, they exist with the monomers, which are small single molecules such as hydrocarbons and amino acids, etc. For example, when we take a large number of ethylene molecules, which contains carbon double bond, carbon, CH2, CH2, when this ethylene is heated, it joins together to form a large molecular weight compound called as polyethylene. The number of repeating units or the monomeric units present in a polymer chain is called as degree of polymerization. It is obtained by dividing the molecular weight of a polymer by molecular weight of a monomer or the molecular weight of a repeating units. The degree of polymerization generally represented by dP, and it is given by the equation dP is equal to capital M by small m, where capital M is the molecular weight of the polymer and small m is the molecular weight of the repeating unit or the monomer. By using this degree of polymerization, we can determine the molecular weight of the polymer also by using the equation M is equal to small m into dP. The repeating units or the repeating unit is a part of a polymer, and it is its repetition by linking together successfully results in a polymer. The functionality is the number of reactive sites on a monomer. The number of functional groups present in a monomer is called as the functionality. For example, in glycerine, the number of functional groups are 2, as one is carboxylic acid and another is NH2. Therefore, the functionality of glycerine will be 2. Similarly, in glycerol, there are 3 hydroxyl groups are present. Therefore, the glycerol will be a trifunctional. For the monomers having double or triple bonds, the functionality is the number of hydrogens or the halogen atoms which can be added across these double bonds. While for some monomers, the number of replaceable hydrogens indicates its functionality. Depending on the functionality of the monomers, we get either linear, branched, or three-dimensional cross-linked polymers. We can classify these polymers on a number of ways. Depending on its physical properties, the polymers with high degree of polymerization are known as high polymers, while those having comparatively low degree of polymerization are known as oligopolymers. The molecular weights of polymers are generally in the range of 5,000 to 2 lakhs approximately. Hence, these polymers are also known as macromolecules. The total number of single monomer units, which is represented by N, combined together to form a polymer is known as degree of polymerization, and this degree of polymerization will affect the physical properties of the polymers. Natural polymers are obtained from the natural origin, for example, wool, silk, cotton, rubber, proteins, etc. Whereas the synthetic polymers are the man-made polymers like polyvinyl chloride, polyethylene, Teflon, nylon, etc. The second classification is based on the backbone chain of the polymers like organic and inorganic polymers. The examples of organic polymers which contains the carbon-carbon backbone are PVC, that is polyvinyl chloride, polyethylene, Teflon, etc. Whereas the inorganic polymers are polyphosphazine, silicones, etc. Based on the nature of the monomers, the polymer can be a homopolymer in which a polymer contains an identical monomers. Whereas the second type is the copolymer, and the copolymers are the compounds formed by two different small molecules that are monomers. For example, in the polystyrene butadiene polymer, one molecule of butadiene combines with one molecule of styrene, and the product obtained acts as a monomer to get the polymer. For example, here in this type, if we take A as a polystyrene and B is a polybutadiene, then both these polybutadiene and polystyrene will act as monomer, and these monomer will join together to form polystyrene butadiene. The different examples of copolymers are random copolymer, alternating copolymer, or block copolymer. In random copolymer, the different monomers will be randomly placed one after the another. Whereas in alternating copolymer, both the polymers monomers will join together one after the other. In block copolymer, blocks or the groups of the monomers will be joined together one after the another as shown in this type of polymers. The next type of classification for the polymer is based on the arrangement of the monomeric units. On the basis of arrangement of a monomeric units in a polymer, these are named as either linear polymer, branched polymer, or cross-linked or 3D structures of the polymers. Some examples of linear polymers are rubber, polyethylene, cellulose, polyvinyl acetate. The polyethylene may also have a branched chains. The vulcanized rubber is the best example of cross-linked polymers with sulfur-sulfur cross-links are joined together regularly. Due to the cross-linking, polymer structure becomes three-dimensional, cross-linked, or the network polymer. This makes the polymer very hard and rigid. You can see the arrangement of the linear, branched, and cross-linked as well as the network polymer in this figure. The polymers can also be classified based on the atoms. If the main chain of polymer is of same atoms, it is known as homochain polymers, while if it is of different atoms, it is known as heterochain polymer. For example, if a polymer contains all carbons in its backbone, it is called as the homochain polymer. Whereas if there are different atoms like carbon and oxygen in this example, they will be called as the heterochain polymers. Homochain polymers are generally obtained by addition polymerization. For example, polyethylene, polystyrene, etc., in which all the carbon will be joined together. And the examples of heterochain polymers are nylon 6 or polyphenylene oxide, etc., in which carbon and nitrogen will be present in a backbone. Based on the effect of heat, polymers are of two types, thermoplastics and thermosettings. There is one more class, elastomers is also existing in between these two. The thermoplastics are linear or branched polymers which can be melted when heat is applied and can be molded into any shape with processing techniques such as injection molding or extrusions. These thermoplastics are mostly recyclable. The most common examples of thermoplastics are plastics like bottles, grocery bags, water piping, rope, fishing lines, car parts, etc. Silk and cellulose, polylactic acid, etc. These are the examples of natural thermoplastics. Different codes are used to represent these thermoplastics like PETE, which will be labeled on the soft drink bottles, LDPE, which will be used for plastic bags, toys, etc., PVC for water pipes, and HDPE for milk jugs. Thermosettings or the thermosets. These thermosettings are normally rigid materials and they are formed by network polymerization process in which a chain motion is greatly restricted by a high degree of cross-linking. These thermosets cannot be reshaped once they are formed. The examples are epoxy resins or the epoxy polymers. The uses of these thermosettings are used in high temperature electrical applications, superglue, countertop laminates, epoxy resins, tires, etc. These thermosets cannot be recycled, they burn or scorch with heating. The natural thermosets are vulcanized rubbers. The third type is called elastomers, and these elastomers are cross-linked rubbery polymers that can be stretched easily up to 3 to 10 times of its original size. They rapidly recover their original dimensions when applied stress is released. They have low degree of cross-linking and they are generally used in examination gloves, rubber bands, bouncing balls, etc. These elastomers are also not recyclable. They degrade when heat is added. The examples of natural elastomers are natural rubber, latex, etc. Based on the configuration of the polymers, they can be classified as isotactic polymers, atactic polymers, symbiotic polymers, or eutactic polymers. The tacticity of the polymer is nothing but the configuration of the macromolecules in a polymer. The isotactic polymers are all the substituents are located on the same side of the molecular backbone. Whereas in atactic molecules, the head to tail configuration is random. That is, the functional groups are arranged randomly. For example, in polypropylene. Whereas in symbiotic polymers, the arrangement of the side group is alternating fashion. For example, the Gutta Parsha. In eutectic polymers, the substituents may occupy any specific sequence of positions along with the chains. These are the different examples. Like in isotactic, same type of groups are present on one side. Here, all the hydrogens are there on the same side, and all the phenyl rings are there on the another side. Similarly, in symbiotic, there is a different arrangements one after the another but in a same manner. Whereas in eutectic, there is a random arrangement of the substituents on the backbone of the polymer. The next type of classification of the polymers is based on the interaction with water. The first type in this is non-biodegradable hydrophobic polymers. These are inert compounds and are eliminated intact from the site of application. Whereas the second type is hydrogels. These polymers swells but do not dissolve when brought in contact with water. For example, polyvinyl pyrrolidine. And this type of hydrogels are generally used in diapers, pads, etc. Soluble polymers are of moderate molecular weight, uncross linked polymers that dissolves in water. For example, polyethylene glycol. Biodegradable polymers, these slowly disappear from the site of administration in response to a chemical reaction such as hydrolysis. For example, polyacrylic acid, polyglycolic acid, etc. The polymers can be named in a number of ways. Like based on the source of the corresponding monomer, they can be called as polyethylene, polyvinyl chloride, polyethylene oxide. In polyethylene, the source will be ethylene, therefore it is called as the polyethylene. In polyvinyl chloride, the starting material or the monomer is vinyl chloride, therefore it is called as polyvinyl chloride. Similarly, as per the IUPAC names, the polymers are named like polymethylene, poly-1-chloroethylene, polyoxyethylene, and here the IUPAC name of the constitutional repeating unit is used. The functional group name system, according to the name of the functional groups in the polymer backbone, the polymers can be named like polyamide, polyester, etc. In polyamide, the amide functional group is present in the backbone, and in polyester, the ester group is present in the backbone. Based on the trade name, the commercial names can be used and they are given by the manufacturers like Teflon, nylon, etc. And in some time, the abbreviated names of the polymers can also be used like PVC for polyvinyl chloride, PET for polyethylene tetraphthalate, HDPE for high density polyethylene, and LDPE for low density polyethylene. This slide represents the historical development in polymer chemistry. The Berzelius first used the term polymer in 1833, and in 1839 the first polymer was synthesized, that is polystyrene. In 1860 polyethylene glycol and polyethylene succinate were invented, and in 1900 the scientist Leo Baekeland synthesized phenol formaldehyde resin. In 1920, Hermann Staudinger proposed a structure for polymer, that is long chain molecules, for which he won the Nobel Prize in 1953. Again in 1939, W. H. Carothers invented the nylon synthesis. In 1963, the Ziegler-Natta invented a new phenomenon, that is the stereoregular polymerization. Similarly, in 1974, Paul Flory invented the polymer solution properties, and in 1984, Bruce Merrifield proposed the method for the solid phase protein processes. All these are the very remarkable and noticeable inventions in the history of the polymers. The description box, the link is given for the detailed notes and the question bank for this chapter.